This presentation is delivered by the Stanford Center for Professional Development.
Okay, let's get started. Well, today we have a very nice video, actually. This is one of my favorite videos, and I think you, let's see. If we could have the light up, please, the projectors. Well, it's not finished. Continue. Keep the light up, please. So, simulations does not always work. In robotics, it's very important to remember that experimental validation is very important. Yes. Okay. That was quite amazing performance of this robot. Let's go back to control. So, I'm sorry for the figure on the left. It's a 2 degree of freedom manipulator, revolute, and last time we saw how we can develop a PID controller for a 1 degree of freedom and then deal with the control of that robot. If we add 1 more degrees of freedom, that is, if we have a robot with some dynamic coupling, we are going to see that the performance of a PID controller is not going to be satisfactory, especially if we are tracking a trajectory. So this equation of motion you're familiar with, I'm going to rewrite it in 2 equations. So here is the equation of motion, and you have 2 joints, so the vectors are 2 by 1, and the mass matrix is a 2 by 2. So if we rewrite this equation in two equations, now you're probably more familiar with this form. So what do we see? We see here sort of mass acceleration or inertia rotational acceleration equal torque, but there are all these additional terms that are appearing. So essentially, the acceleration of joint 2 or link 2 is appearing in the first equation and is affecting the dynamic behavior of the first link. So as you accelerate, you have a coupling through M12, and that is producing disturbance forces or inertial forces on the first joint. We have opposing forces coming from the acceleration of joint 1 on joint 2. We have on joint 2, what kind of forces here? Come on, you have immediately to recognize this form. What kind of forces are these? Centrifugal forces. On the top, Coriolis. So product of velocities, Coriolis, square of velocities, centrifugal, and these gravity forces. So all of these are going to have an impact on the robot, and it's really difficult to imagine that these are zero or treat these as disturbances. They are going to be there, and as you accelerate one joint, you have an effect on the other joint. So really the system that we talked about, this controller that is controlling a joint, a link, is going to receive disturbances coming from the gravity and coming from the motion of the other link. You see that? Which means that while to ignore it, we need to really treat these as disturbance forces, but these are large disturbance forces. And the only way you can deal with the rejection, as you know, is increasing KPs to reject your disturbances. So treating the system as an independent joint is not a valid assumption. And in fact, most robots today in industry still use this scheme. They say, okay, I'm not going to care about the motion of joint 2. I'm going to put a controller with large gains so I can control each of the joints separately. Whereas in reality, the n degree of freedom system, each of those joints is receiving those coupling forces. And these coupling forces are interacting. So there are something, not only disturbances, but the fact that they are interacting, there is something about the stability. How can we say that this system is stable if we are controlling it with a PD controller? Right? Because you have this interaction taking place between the links as they move. So the stability of a system that is highly nonlinear and interactive in the way we saw is not evident. How can we prove that this system with a PD controller with all these disturbance forces coming from the interaction is stable? Anyone? Yes? Energy. So in fact, what we're going to do to prove this is to go and do an abstraction to see what kind of energy we are putting in the system and how we can show that the system is stable. In fact, in the late 70s, there were a lot of papers written about the PD control stability to prove that, yes, the system can be stable just with PD controller. So instead of looking at the equation in this form, a torque equation with a controller that is this is a vector PD. It's not just a component. It is applied to all the joints. So what we're going to do, we're going to go to an equation you are very familiar with, which is which equation of energy we're going to use? The Lagrange equation. So instead of analyzing this component, we will go and write this equation in this form. So now we are doing an abstraction to a scalar quantity, which is the energy, the kinetic energy and the potential energy. In this form, we can analyze the impact of those controls we are applying to the system. And immediately we will see their effect. So when we apply the torque equal minus Kp, Q minus Q desired, essentially we are putting a first term, this proportional term is a gradient, right? It's a conservative force. It's a gradient. And this gradient is coming from the potential energy of the springness Kp, which is varying on different joints. Kp is a matrix. Diagonal matrix, you can imagine you have different Kp's for different joints. But still, it's a gradient of some energy. So now, how can we prove the stability of the system? It's now much easier, yes. So what we are going to, decreasing or equal to 0, or basically, what do we have here? You see a V here and a V there. So what you are doing is basically by adding this, if you move this to here, you can see the effect of your control. Your controller is essentially, here is the inertial forces, and your control is modifying the initial potential energy of the system, which is the gravity forces, to change it to Vd, this potential energy desired. So instead of having your energy making you fall down, now you have some energy that is going to help you go to those desired goal positions. In addition, on the right-hand side, we have a term that is minus kv q dot. So this term is going to bring additional stability. That is, it's going to bring asymptotic stability because it will dampen and oppose the motions along the q dots. So you remember this condition, that these forces are acting against the velocity. So as long as your kv is positive, this condition is satisfied, and we can show that essentially this system is going to achieve this motion. So you will go to the minimum of that potential energy, and because of this term you are going to be able, because this damping term, you are able to asymptotically stabilize your system. So yes, a PD controller is stable. But this doesn't tell you anything about the performance. It tells you, yes, you're going to move and reach that configuration, but along the motion you have all the coupling. So in here, whatever coupling you have, it is going to appear in the kinetic energy derivatives, and that will produce the inertial forces. So if you're moving to a goal position, there is no problem. You can move and reach that goal position. And you will have a small offset because of the gravity. You can, in fact, put in Vd some compensation of the gravity and take it out, so you can reach that goal position. But the performance along the trajectory are not going to be, if you are tracking a trajectory, are not going to be good. So how do we evaluate our performance? What are the parameters in this controller that affect the performance? Yes, the Kp and the Kv. The Kv allow us to dampen the system, and Kp allow us to reject disturbances. So what would you like to do in order to reject the disturbances? as large as possible. So you need high gains, right? So if you have, if you're able to implement high gains, then you get better disturbance rejection. However, your gains are limited. In practice, you start cranking up your gains and you start, we had the simulation, and I showed you as we increase the gains, we reach a point when we start vibrating, and this was only a simulation. In the real system, what do we have in the real system? We have structural flexibilities. We have flexibilities in the links. We have flexibilities in the drives. So if you take the Puma has those motors placed inside, and they are connected to the joints through rods, and they have flexibilities. And when you start cranking up your gains, what's going to happen? Higher gains, you start to have a closed loop frequency closer to your flexible structural frequencies, and that leads to instabilities. You excite those modes. So if you have flexibilities, you have to make sure that your gains result into closed loop frequency below your structural flexibilities. And not only that, you have time delays in the actuation. So you're sensing, you're measuring the encoders, and then you are going to compute your controller, and then you are sending this controller to the motor, and the motor has some time constant, so you have some delays. And you have also the sampling rate. The servo loop is running with some sampling rate that needs to be quite high. And this is not anymore a problem. It used to be a problem when we had slower computers, but now the CPUs are so fast that this is not anymore an issue. So here is a rough idea about the limitations you have. If we take the resonant mode, the lowest resonant mode on your system, you have to make sure that your omega n is lower than half of that resonant mode in order to be able to avoid catching with those structural flexibilities resonant mode. In terms of delays, you are limited also by 1/3 of the frequency of the delays. Well, as I said, this is not anymore a problem. So the key issue is this lowest structural flexibility in your system, and it is there. And believe me, you start cranking these gains up, tuning your gain, and you start to hear the vibrations. So it's very difficult to achieve high gains. And remember, the delay is in time, it's 2 pi divided by the frequency is 2 pi divided by the time of the delay. This tau is time. Okay, so what is the solution? If we cannot really crank up those gains so high that we will cancel all disturbances, dynamic disturbances, what is the solution? So if you remember, the problem is like this. At each of the joint, you are getting this disturbance force. So what should we do? I have the model. I have good estimate of MIJs, good estimate of the gravity, because you just did a lot of homework with dynamics. So you know how to find the structure. You can eventually identify the constant involved, the masses, the center of mass. You can measure all of these. And then what can you do? Oh, I'm sorry. You're sitting so far on the left, couldn't see.
If you use a model of your plant, especially the non-linear parts of your plant in your control law, and effectively you can turn it, and also if you diagonalize the mass matrix, you turn it into a decoupled, a very simple 1/s² plan.
Yeah. Well, I mean, the idea is right. Basically, let's use this model. If we know the dynamics in advance, we can use this model. And essentially, what do we need to do? We need somehow to counter this force. So how we counter this force? We compute it and like inject it back in the system to counter it. Now, the diagonalizing the matrix is not really the issue, because if you essentially you want to compensate for the coupling forces, so what you want to do is essentially for joint 2 somehow to compensate for those terms, these coupling terms. So this brings us to something we discussed earlier. You remember this unit mass system that we can achieve by compensating, by scaling our controller with a gain that is proportional to the mass, m alpha plus beta, or alpha f prime plus beta. You remember that? Well, now we are going to extend it there. And what we're going to do is to go to that first equation in the matrix form, and we are going to say we are going to take a torque that is proportional to the mass matrix. So our torque will be some estimate of the mass matrix times torque prime plus a beta that compensates for V and the gravity. And this is what we're going to do. Oh, nice. What was this? So what we're going to do is we take this model and we imagine that somehow, after a lot of identification work, we identified some estimate of the mass matrix. So the mass matrix, actually, you know its structure. You know the structure, but it has in it parameters, inertial parameters, distances that you don't know exactly, but you know approximatively within epsilon. So you take an m hat of the mass matrix and you select a controller torque prime. So this is alpha f prime plus beta. So think about just taking a controller that compensates for the gravity estimate. So essentially what you're going to say, if this is perfect, I take this out. So this is not anymore in the equation, right? If this estimate is perfectly equal to this, this will drop. Your controller will be m acceleration equal m hat torque prime. If m is exactly equal to m, your unit acceleration is equal to torque prime. So basically, you are able now to drive the acceleration theta double dot with theta prime, with torque prime. And your torque prime is now the input, the control input of the decoupled system, the unit mass system. So if we select this structure, and if we apply this structure to the equation, and if we multiply this whole equation by m minus 1 to bring theta double dot out, what you obtain is m minus 1 m hat torque prime plus m minus 1 v minus v hat g minus g hat. Okay? Suppose that g hat is identical to g. Just suppose for a second. And v hat is identical to v. The second term is going to disappear. Will be 0. M minus 1 and m hat. If m hat is identical to m, m minus 1 m is identity. So with perfect estimate, this is your behavior. Magical. So essentially, the nonlinear dynamic decoupling of a multi-body system relies on this structure. If you use this structure to take a controller, any controller, not a PD controller, any controller you want, And this controller is going to be scaled by the mass matrix and add to it nonlinear dynamic compensation to compensate for the terms, nonlinear terms in your controller. Then you achieve dynamic decoupling with a behavior that is controlled by torque prime, and torque prime now is controlling the unit mass, unit inertia of all your degrees of freedom. So if you select your torque prime in this way, like this is a trajectory tracking to track theta desired, theta dot desired, and theta double dot desired, then you are going to be able to achieve a closed loop in this form if you have perfect estimates. Now, in reality, do you think we will have perfect estimate? No. But if we don't have perfect estimate, we have to have good estimates in order for this to work. So you will have a difference between V and V hat, a difference between G and G hat, and some difference between there, and that will bring some epsilon error, disturbance. And this disturbance will appear here, right? It's not going to be equal to 0. You will have some disturbances. So what is then going to be important is that your Kp prime and Kv prime to be selected so that you reject those disturbances. But those disturbances are much, much smaller than the initial dynamic coupling that we saw before the compensation and the decoupling that we use in this structure. So this controller, as long as your estimates are reasonable, is going to give you decoupling with some errors, and you still need relatively large gains, but much, much smaller gains than the one will be needed without any dynamic compensation. Okay? Now, it turned out that you should be able to identify your dynamic, the rigid part of the system's dynamics to a large extent, to a small epsilon. So those epsilons are small. However, in the initial equation, we are neglecting. What are we neglecting on this first equation? We are not showing here. This is the system, the robot. What is missing there? No, friction. So there is friction, there is actually nonlinear friction that is difficult to model, and there are a lot of other nonlinearities, and then you have the higher order dynamics that we are not modeling. We are modeling just second order dynamics. The flexibilities are not modeled. So you are going to find limitations here. You can try to compensate for part of the friction forces, but it's not going to be perfectly compensated for. So higher gains are very important here. In practice, compensation for the gravity, suppose we do not, we made a big mistake with the gravity. The gravity is, we estimated the gravity and we were wrong, and we selected G hat to be 0. What is the effect of that on the robot? So you will have just like a sort of constant torque offset that will be divided by your Kp prime times m. So that's not going to affect the stability. You will just reach the final goal position with little error. So what is the effect of m minus 1 and m hat? Well, if you make a mistake in the estimate of the mass matrix, it's going to sort of scale up or down your gain, your Kp. So your Kp will be, with this structure, m hat times torque prime. m hat times torque prime means kp prime is multiplied by m hat. And if that estimate is little wrong, you are changing your gains up or down. So it is sort of like a gain that you will have. What about v and v hat? So estimate of m hat, if you make a mistake in the estimate of m hat, as long as m hat is positive definite from your structure, you shouldn't make a mistake. If you make an estimate, the effect of it is just scaling up and down your gains. It's not going to affect too much the stability as long as you have a positive definite metrics. What about v? If you make a mistake in v hat. So what is v? V is function of theta and theta dot. You make a mistake in v hat, which is coming from your estimate of theta dot hat, you're estimating to compute v hat, and that might be really dangerous because v is function of velocities. And if you make a mistake in your estimate of centrifugal Coriolis forces, you might create sort of negative feedback in velocity, which could destabilize the system. So in fact, if you do not know v hat well, it's better just to treat v hat equal to 0 rather than making a wrong estimate. So beside v hat, errors in g or in m are not a problem for the stability, it's v hat. And if you don't have a good estimate, you can just use a 0 estimate of v hat. Okay. So this is the overall control system. Basically what we are doing is we are doing a feedback that is compensating for centrifugal, Coriolis, gravity, and all these forces. And then we are scaling our input. So this is torque prime. It's scaled by m hat, and we are adding these to produce the torque. So the torque is m hat times torque prime plus those estimates. And then we are able now to compensate for centrifugal Coriolis gravity forces and scale our gains and decouple the system. And the overall behavior of the system will be decoupled. So now we are able to control our robot, but what we did here, we controlled our robot in terms of its joint motions. Where do you get these trajectories? So you have your camera, you have your hand, and you want to move to the goal position. Remember our initial problem. You want to move there. How do you compute all these trajectories for the joints? And this brings the problem of inverse kinematics that you need to use to transform your task description in terms of joint trajectories. Well, this brings us to task-oriented control, where instead of thinking about the inverse kinematics as a way to transform the trajectories, we go directly to controlling the task. And I talked about this earlier, but let's take a simple example to illustrate this problem. So here is a robot, a mobile manipulation platform, and our goal is to move this robot and a factor to move it to this goal position to grasp this object. So how do you do that in joint space control? Quickly. We have a lot of things to talk about, so quickly. Think about it. What do we need to do in order to go to that goal position?
Maybe translate positions to joint orientation.
Well, I mean, essentially, if you go like a little bit to a higher abstraction, what you can say, well, I need to imagine the final configuration where I'm going to be. And in fact, I need to imagine all the configurations of the robot. I need to find this configuration. How many configurations like this you can have in this case? To reach this configuration, you can be here, you can be there, you can be in infinite ways. So the question is, you have infinite ways from starting from here to go to there because of the redundancy. And it's really difficult a priori to say which one is better. It's really difficult when you have redundancy to resolve all that redundancy and decide about it ahead of time. And if you do that, actually, you lose a lot of inertial properties that you can use in the control of the robot, as we will see a little bit now and much more later when we analyze the fact that this base is heavy, this arm is lighter, and if you are able to use this fact of macro structure and mini structure and combine them, you are going to be able to better use the reduced effective inertias that are coming from macro mini structures and controlling the robot in a much better way. That is, we will see that we will be able to really reach rapidly and then stabilize the macro structure. Reach with the fast dynamics of the system and then stabilize the system. So how can we control this differently? How can we move from here to the goal position without deciding a priori what final configuration we're going to have? Okay.
What the structure does.
Exactly. And this was the idea I found many, many years back, which was to say, I mean, I don't need to know exactly how the structure is going to move at this time. Let's just move the end effector. So pull on the end effector. And pull on the end effector is very easy. You just apply the gradient of a force that is pulling on the end effector. Right? So if you virtually apply a force at the end effector that is the gradient of this force, which has its minimum at the goal position, essentially this end effector is going to fall in this potential energy and it will move towards the bottom, right? Well, you don't know exactly how it's going to move. It might, because this is not a point mass you're dropping in a potential energy, it's a multi-body system. And this is what we call task-oriented or operational space control. Operational space control relates to what we are trying to do with the robot. It could be the end effector. If we have multiple arms, it could be both effectors, or it could be any set of descriptions related to the task. You have a question?
Yeah. Do you have to give priority to different joints when you do this, or is it factored into the energy equation?
So let's see it little by little, and then you see how you can put priorities, how you put constraints. On Wednesday, I will describe how this simple concept of a combination of an attractive potential energy that pulls you to the goal, combine, and now this is what is interesting, is I'm going to move to this goal, right? And this is the goal. But as I move, there are obstacles on the way. Now I can apply repulsive forces on those different links that are interacting with the environment to move them away. Which means that if I was doing this in joint space, I need to do the whole motion planning ahead of time to make the decision about how to move. But suddenly an obstacle comes and moves, or I discover that this obstacle is not there. How can I readjust and recompute, or the inverse kinematics? I would need to do replanning in real time. Whereas in here, you are able directly to affect those constraints. So we will see a lot of issues that relates to how, in real time, We can deal with many other criteria related to how far away I would like to keep the body of the robot from there, what type of angles, orientation I would like. You can add all of these as well. But this will bring us to how we control a redundant manipulator. And these are issues that will come in advanced robotics next quarter. But essentially, the basic concept is very simple. The basic concept is to say, I want to move to those goal positions. You can have goal positions for the end effector, for the base, for any part of the robot. And then I need to protect the robot from touching anything, so I apply these repulsive forces, and you drop the system in that field, and it will just move and go there. Now, I didn't talk anything about the dynamics, but essentially this is the basic concept. Now, how can we apply this force? So the gradient of a V is a force. How do you apply this force to the motors? So you want to apply a force here, F. What would be the corresponding torque? So it will be torque equal F. We need something to relate this force to the torque. J transpose F equal torque. That's it. So if you just apply a J transpose F, where F is this gradient of your goal position in X, you apply this to the system, and the result is going to be that you will move there. And it works. Again, it doesn't deal with the dynamics. Your motion is not guaranteed to be decoupled. You are just like pulling all these links and moving. So what we need to do is really to look at the dynamic properties of the system and evaluate how the system is behaving when we are moving in those ways. The other interesting thing about this controller is, and this is really the fundamental property of those controllers, is the fact that now you have a way to deal with contact. Because when we are going to move this object, so I grasp the object, and suppose the task is to move this object over the table while it's in contact. And I need to push on the object. I'm doing some assembly, and I'm touching the object and applying a force. To apply a force in some direction, it's very easy. If you know your contact forces, you do J transpose F contact. But now, to move, we are translating the control for motion in terms of F motion. So essentially, we are unifying the two problems. In one problem, you just add them. And you take the sum of the two, and now you have a unified way to control both motion and forces. You have to make sure that your contact forces are in the proper space. That is, in this case, it's the vertical directions, and your motion control are in that space. And when you go to more complex contact, you have to do some selection and project your controllers in those spaces. So the dynamic problem that comes with this is quite interesting. It is a problem that comes from the fact that when you apply this force to the end effector, and as I said, this is not a point mass, this is a multi-body system, you are going to obtain an acceleration. So if you have a point mass, and if you apply a force in the x direction, this is the x direction, your acceleration will be along the same direction. In this case, your acceleration is going to be somewhere else because of the coupling. There is a coupling between F and the acceleration. So you need to find the relationship between forces and acceleration at this point. There is a mass matrix associated with this X that allows you to evaluate the mass properties in the different directions and the coupling between them. So if I'm here, and if I push in this direction, I will feel sort of an effective mass of, like, say, 5 kilograms. But at the same configuration, if I push in this direction, the mass is different, 2 kilograms. And if I rotate about this axis, I will feel some inertial force that is different from this one. And this is your mass matrix, basically. This is different from the mass matrix that we were talking about, the inertial properties in joint space. The effective inertia about this axis that is varying, the effective inertia about this axis, and the coupling between them. Now, if I push in this direction, I will see this motion, because there is coupling between the y direction and the z direction, and the x direction, and the rotation between them. But if I am able to model this, then, well, there is centrifugal Coriolis gravity forces as well. So we are just going to be able to model the dynamics in that space for this point. And if we obtain this model, which is simply a relationship between forces and acceleration, velocities and positions, a different configuration, you have different properties. Once you have this model, you can do the same thing we did with controlling the robot in joint space by decoupling, making estimate of this, decoupling, and making an f star or f prime. Now we select an f that is proportional to the mass, the estimate of the mass matrix, with compensations of centrifugal, Coriolis, and gravity forces. And then you can control it. You find your f, you multiply it by J transpose and transform it into term of torques. And suddenly now you are directly controlling your robot in operational space, in the space of the task. And that would allow you to control directly your errors in that space. So your force control will be function of those estimates, in the same way, with the same structure that we saw just earlier. Okay? So to discuss this model, I'm not going to go to the redundancy. We can do that in the redundant case. And as I said, we will discuss this more in advanced robotics. But essentially what you are doing, you are making an abstraction to the robot, focusing on the task, which is, in this case, this frame at the end effector. And in the non-redundant case, you select a set of generalized coordinates, which are going to be your x, y, z, alpha, beta, gamma. If you have a 6 degrees of freedom and an end effector with 6 degrees of freedom, basically what you're saying, instead of selecting q1, q2 to q6 as generalized coordinate, I'm going to select x1 to x6 as generalized coordinates. And then you write your equation of motion with respect to those coordinates. So here is your generalized coordinates now. You write your equations of motion with respect to those coordinates. We're taking the partial derivative with respect to x. We're talking about x dot. We're talking about not torques, but forces acting along x, y, z, and the different components. And if you do this computation, you end up with the similar model, identical model. I mean, I'm changing q in x now. You have a similar model, but now capturing the properties at your end effector. So these are the definitions. Basically, everything is the same, except that now it is related to your task. Okay? So the relationship between these dynamics, the mass matrix M of inertial properties at the joints, and the mass matrix at the end effector. How can we establish those relationships? Again, energy. Yeah. So what is the kinetic energy of a manipulator described with respect to joint space coordinates, with joint velocities? 1/2 Q dot transpose M Q dot. You agree? All right, I just changed my coordinates. What is the kinetic energy described with respect to X dot? Supposing the robot is non-redundant, and these are generalized coordinates, so they capture all the motion, so it's in X dot. So what would be the kinetic energy? 1/2 X dot transpose mx X dot. You agree? Is it the same kinetic energy? Yeah. So we have an identity between the two. So if we write this identity between the two, see how beautiful this is. Once you go to the right abstraction, it's very easy to extract properties. If I say the kinetic energy written in this space should be equal to the kinetic energy written in this space, I have already resolved the relationship between what is mx related to m. Do you see it? What should we do now to resolve it? You see this X dot and Q dot? What is the relationship between the two? The Jacobian. So if I substitute X dot with JQ dot, we have the answer. So I'm just rewriting the same identity between the two. And the mass matrix we computed in joint space is related to the mass matrix in operational space by just M is equal J transpose M JX. Which now you can compute this as a function of this by multiplying from the left with J minus and from the right by J minus transpose, which gives you Mx equal J minus transpose M J minus 1. Okay? That was easy. Do you agree it was easy? So, in fact, once you computed your Mx, then you can see that, in fact, your centrifugal Coriolis forces, they are not J minus transpose. They are not just, these forces are not J minus transpose V. They are J minus transpose V minus this quantity. So actually, in fact, when you look at this as a torque and compensate and decouple centrifugal forces in joint space, you are not really decoupling the end effector centrifugal Coriolis forces, because the relationship between the two is different. By the way, H is just J dot Q dot. So this H appearing there is this. So this is the relationship between the two. The gravity in joint space and gravity in operational space are related just by J transpose minus. So the gravity is a torque, and you compute the force. So if you multiply by J transpose Jx equal to J, basically. Minus transpose means it is a minus, it is J transpose minus 1 or J minus 1 transpose. Okay? So the relationships between the two are very simple. Well, they were not simple to find, but they are simple. Okay, here is an example. I think we can quickly go over this example. We saw this example before. Remember, we saw it in joint space, and we computed the dynamics through this. And all what I'm doing now is going and finding the Jacobian. So this is your Jacobian, which I'm putting in frame 1. And I'm writing now, so this is the Jacobian in frame 1 of this robot. And now if you remember from joint space dynamic of this robot, the mass matrix was diagonal and decoupled for this robot. Now, if I'm computing the mass matrix in frame 1 for the end effector position, I need to multiply by J minus transpose and J minus 1. And that turns out to be, again, a diagonal matrix like this. So in frame 1, the mass properties, so now let's think about if this mass matrix for the end effector makes sense. So this robot has the following properties. We said it has a mass of link 1, M1, a mass of link 2, M2 at this location. And now I'm looking at the mass properties, that is, what is the effective mass when I move in this direction, because I'm representing this in frame 1, which is this. So if I move in this direction, what would be the effective mass I would see when I'm moving in this direction? And what is the effective mass when I'm moving in this direction? So let's see if this makes sense. So if I'm moving in the x1 direction, this direction, what do you expect the mass to be? This is the end effector. I'm moving in this direction. What do you feel when you move in this direction? M2. Well, this is what you see here. Correct. If you move in this direction, what do you push? What do you carry? What masses are moving with you? M2 plus something else, because you are pulling, you have to move this. So you get another term, M2 plus something. What is this something? This something is sort of this M1 reflected there. And that depends on the distance. Right? So essentially what you are doing, actually M2 prime, is taking this distance, dividing it by 2, and computing all the inertias related to M1, the inertias of link 2 and link 1 that appears here, and all as if they were just a mass. So this is what you're doing. When you go to the mass matrix at a given point, you are looking for this mass that produces all these effects that are equivalent to those effects that you see if you had all these masses. Make sense? Good. So let's now go from this diagonal mass matrix in frame 1. If I go to frame 0, I need to multiply it by the rotation matrix, right? Rotation matrix. Look what happens. In frame 0, the mass matrix is not diagonal. So if I'm moving this structure along the x direction or y direction, I'm getting like the eigenvectors. But if I move in any other direction, there is coupling, and this is the coupling. So the properties that you see in joint space, they could be decoupled even for some robots. When you go to the real space where you are doing the task, the properties are different. And essentially here what we see is in the direction x we have M2. So if you draw the ellipsoid, you see square root of M2. And in the other direction you have M2 plus M2 prime. But in any other direction you are basically getting the square root of the magnitude in that direction, like this. Okay? So how do we control this robot? In fact, well, on Wednesday I will show you a little bit how those properties are through the ellipsoid inertia and the limitations of the different characteristics. But let's do the end effector control now and see how we're going to show that just applying this controller with a sort of a force is going to lead to a stable behavior. And then see the problems, how we can go to dynamic control. So when we apply F to the system, essentially what we are doing is we are saying, I'm going to apply a force F, and this force F could be in many different ways. We are saying let's apply a gradient of a potential energy. So the gradient of the potential energy that depends on the goal is going to be 1/2 kp, this vector x minus x goal transpose x minus x goal. So if you take this force and say this is my force, it's a gradient of this potential energy, the result is this. Essentially, what I did in addition, I made an estimate of the gravity V. So I put in my gradient some estimate of V hat of the gravity. So I'm compensating for the gravity. So what happens is the initial system that was K minus V is now transformed into K minus V goal. It's sort of like I have my arm. I would like to move to this goal position. Instead of having the robot without any control, if the robot you drop it in the gravity field, it will fall like this, right? Now I'm changing the gravity. It's going to fall there. That's it. So this system is stable. It will oscillate about V goal. It will oscillate, but stable. Right? Instead of oscillating about the minimum of the gravity field, it will oscillate about the minimum of the artificial potential field you are putting about your goal position. So how do we stabilize it? Quickly. Damping. How do we select our damping? To oppose x dot. And to oppose x dot, we put forces that satisfies this condition again. So it's very simple. You just select Fs to be minus kV x dot with kV positive. You have your control. So this is my estimate of the gravity, to remove the gravity. And this is the proportional term in x. Directly, you take the proportional term, and you have asymptotic stability. No, you have stability here. And when you put this additional damping, you have asymptotic stability. All right? So let's take our 2 degrees of freedom and now treat them with this controller. This is the dynamics. Someone get a phone call? Let's write the controller. So are you following so far? Here is the dynamics in operational space. This is your controller. Let's look at the behavior. So I'm just splitting this first equation in 2 equations, x and y. So this is the behavior in x, and the second equation is the behavior of y. And what you see is that I'm just copying this from the real mass properties of the mass matrix in operational space for the 2 degrees of freedom. So what you see is that you have m1 cosine square of theta 1 plus theta 2, m2 acceleration, m1 star multiplied by the acceleration. So what do we see? We see that essentially when I'm accelerating, when I'm studying the behavior along the x direction, I have coupling coming from the y direction. And my controller is like this. So what is the closed loop behavior? Well, the closed loop behavior is like this. It's like I have a mass acceleration plus kv x dot kp x, and instead of being equal to 0, it's equal to the acceleration of the second joint and the nonlinear terms coming from the errors associated with centrifugal Coriolis forces, and the same thing for the second joint. I mean, not second joint, second direction. In addition, what about this? Suppose this was 0. These are disturbance forces, right? But what is this? It's telling you that as you move, your mass, effective mass, is changing. You know, your effective mass is very small here. And when you reach this location, do you know what is your effective mass? I'm pulling too much. very small. When you reach here, what is your effective mass in this direction? Infinite, yeah. Basically, when you reach the singularity, this will become so high that you cannot move anymore. It will become infinite. So this is a nonlinear system because also the mass properties are changing. Still, it's asymptotically stable. It works. But you have a lot of disturbances. You need high gains. We cannot achieve high gains. We know why. So what should we do? Come on, we don't have too much time. What should we do? Decision under constraints. What should we do? Use the model to decouple and linearize the system. So nonlinear dynamic decoupling, it's very simple. When you have a model like this, immediately you have a unique structure that will give you the answer. This is your structure. Compensate, take out the gravity with an estimate of the gravity, take out your centrifugal Coriolis forces with an estimate of it, and take your controller to be proportional to an estimate of your mass matrix. That's it. Okay, you have a structure like this. X could be Q. So you will be in joint space or in any other task space. This is your structure. This is your system. On the right-hand side, you have your controller. On the right-hand side, this red thing can be selected in this structure. And once you selected this structure, you apply, and if your estimates are good, you apply it to the system. Your behavior is going to be unit mass acceleration equal f prime. Okay? Unit mass acceleration equal f prime. Now you select f prime, whatever. You have a goal position. You have a motion tracking. You select your f prime the way you want. And because now you have your f there with that structure at the end, so you compute your f prime for the different tasks you have. And then you apply this f over there, not this one. F prime is in here. You apply J transpose F as a torque, and now you are controlling the torque needed to decouple the system and track the desired behavior you're imposing in F prime. Okay? If your estimates are mass hat identity, Vx equals 0, basically we are back to the non-dynamic control system, to the PD controller with potential energy. If you are applying the potential energy at this level, you are reshaping it and adding the appropriate forces to decouple everything. Okay? Good. So if I have a goal position, we saw this controller, but if I have tracking, I know x, x dot, and x double dot, then so for the goal position controller, your behavior is linear and decoupled, and everything is going to let you move to the goal position following this second order behavior. If you have all these descriptions, then your controller will anticipate the acceleration. So you had feed-forward acceleration, like we did in joint space. You have feed-forward acceleration. You have tracking of the velocity, the desired velocity, and tracking of your position error. And the closed loop is like this, which means now you are controlling directly the error in the task space. That is, you have your camera, you are doing visual servoing, you get your x desired in real time, x dot desired acceleration, whatever, from your sensory information, and you are able to track and control your robot to follow the trajectory specified by your feedback, and in real time you are achieving this decoupled behavior. Whereas if you do it in joint space, actually you are controlling a tracking in an error, not EX, you are controlling EQ. And dynamically, this is very different, because the relationship between EX and EQ is nonlinear. So this is what you are controlling now. Whereas in joint space, you were controlling this when you were tracking. Okay. So this is the overall controller. The overall controller is now compensating. It's the same structure that we saw before, but instead of looking at the system in joint space, we are using this J transpose to transform this into the end effector behavior. And now we are compensating for centrifugal Coriolis gravity forces that are modeled for your end effector. And we are scaling with an MX, with the mass matrix of the end effector. And we are controlling the trajectory. So here we control an F prime. Here we get F, which is the sum of scaling F prime by M and adding the nonlinear compensation. And your dynamics now is controlled in task space. Right? And that's what you want. Good. So on Wednesday, we will talk about some additional aspect of the control dealing with compliance and some ideas about force control. And then I'm going to give you a preview of a lot of the research going on in humanoid robotics and in design of robots to work and interact with a human in their environments. So they have to be safe. And we will talk about those issues on Wednesday. In the meantime, on Tuesday, I will see half of the group, I hope, for the review session, and the other half on Wednesday. See you on Wednesday.